Starting already. Okay. Go ahead.
All right, guys. So the topic of today is Astute RAG, overcoming imperfect retrieval augmentation and knowledge conflicts for large language models. Now, for this paper is straightforward. It's one of those beautiful papers. I've been doing RAG now. We have all been doing RAG, I suppose, for the better part of almost 2 years, a little short of 2 years. Nevertheless, and there are tons and tons of papers, research papers and techniques and survey papers that we read, that we incorporate in what we are doing. Every once in a while, you come across a paper like this and you read it and you realize the idea is so beautiful, so simple, it's genius. Why is it that we didn't think of it ourselves? And I really felt delighted actually reading this paper. It is so very easy to understand what this paper is saying. No mathematics necessary. Nevertheless, it's a very effective idea. I mean, as we read through the paper, you'll see that it claims to improve the performance of RAG, and that is very believable, not only from the empirical results they give, but from the obviousness that if you take this approach, it does make very plausible sense that the results that you would get would be better. So now, I'll put it in a broader context before I continue. Is there anybody in the audience who does not know what RAG is, Retrieval Augmented Generation is? Since we all do know what RAG is, I will sort of hasten my way through a very quick sketch of RAG, just to better recollection, and to set the stage for this paper reading. So when we do RAG, typically, in a very simplified or baseline RAG, obviously RAG gets to be fairly complicated. The more we do it, the more complicated it gets. Now, it is made up of two parts. One part is the search. You get a query. The query, you pass it through a set of retrieval search indices. Search index 1, search index SI, K, different search indices, SI, N, different search indices, and most of us do a multi-source query. We will feed it in, and each of these search indices, search index, could be web crawl, it could be a traditional BM25 style search, think Elasticsearch, etc. It could be semantic search in vector DB. And what we do quite often is we send the query as a fan out to a whole set of search indices, each of which produce a set of candidates. So you get candidate collection 1, C2, C3, CK, CN. Right? You get lots of candidates, let's say 10 of them per search index. Now you do have a problem. What you have at the tail end is, in the simplified version, we have an LLM which has to look at these documents, or we'll just call these search results documents, and it is fed also the query, and it is given a prompt template, a prompt, which basically says, in consideration of the facts enumerated below, which is the candidates that you get from search results, answer the user query, and then you get the result. So this is your quintessential picture, or a simplified picture of retrieval augmented generation. The generation part is obviously the LLM part. This is the gen part, generating the answer to the query. And the retrieval part is, of course, this is the retrieval part of it, the retrieval part. Right. Now, when we look at a search system like this, And of course, in reality, what you might have done is you might have put a re-ranker. Let me just put a re-ranker in between here. Re-ranker, because you may not be giving all, let's say that you have 10 indices, but 10 results from 10 indices would be 100 results. You may actually pick only 10 results by re-ranking the candidates coming from different search indices. So this is your basic architecture of a RAG. This kind of this architecture has again, we'll look at it from two different perspectives. One way of looking at it is from information retrieval perspective. When we go to Google and we search for something, we get a list of search results. The burden is on us to read those and find an answer to the question we are asking to our query. Google doesn't read and answer a question. All it does is it gives you a set of search results, which it thinks are pertinent. And so if we read those search results, then we would be able to answer the query. That has been the information retrieval system. All search engines work like that, whether internal document search engines or web search engines. Now, the value of appending an LLM to an information retrieval system is to complete the path. To the extent that these LLMs are language understanding machines, it is a no-brainer to say that if I get a lot of text coming in, a lot of documents coming in which are pertinent, why can't an LLM read those documents for me and then answer the query that I've given? And to be able to do so, obviously completes the RAG pipeline. So that is looking at it from an information retrieval perspective. That, as you know, is in full swing. Today, Google is now embedding Gemini into its search engine. In other words, Google is transitioning from a traditional search system to a full-blown RAG system. Bing is doing that. OpenAI is doing that. Just about everybody is doing that. Perplexity, most of you have been using Perplexity. And so Perplexity is one of the shining examples of how to do it well. There is an alternate perspective that you can look at RAG systems from. The alternate perspective is to ask this question. Given a question, if the LLM does not know the answer, how can we still have it answer? Why would the LLM know the answer? Because the LLM has parametric memory in its weights and biases. Somewhere hidden in the belly of the LLM is a lot of information, a lot of knowledge. You may wonder, is it really true? Because all of those are floating point numbers. We don't see facts squirreled away in an LLM. If you open an LLM, all you see are weights and biases. So where is that repository of fact? In the early days, people used to doubt whether facts are stored in the LLM at all. Subsequently, and in fact, there was a famous situation. The New York Times, a magazine in the newspaper in the United States, observed that OpenAI was essentially giving responses that looked suspiciously like the articles written by New York Times journalists. And they approached OpenAI and said, well, no, this is not okay. This is plagiarism. You did not cite us. You didn't do anything. And I believe, roughly speaking, the way I heard it, OpenAI said, we couldn't be, because the LLMs have no memory. They're just weights and biases. We don't store your articles. We don't use it during answering process. And New York Times did a very simple experiment. They said, okay, we'll give your LLM, your OpenAI, your web ChatGPT, a prompt. We'll give a few sentences from our article and let it go continue and finish it. And what they observed is that it, with fairly high fidelity, managed to reproduce the rest of the New York Times articles. Right? So that, again, you can't argue, and obviously New York Times people were not kidding. They're journalists. They know how to prove a point. They did manage to prove a point that whatever fancy math you may be up to, you may not understand that. Nevertheless, here is empirical evidence that of all the things that your machine could have written, it chose to write the continuation, which exactly is what a journalist wrote. And therefore, it has somewhere memorized it or stored it. So there has been an active area of research. Where does a LLM store its memory? To the best of our knowledge, it is in the feed-forward layers. That is an emerging understanding that we have these days. That and it goes back, if you are interested in the mathematical underpinnings. There is a thing, and there's a lovely article, there's a lovely video that 3 Blue 1 Brown has come up with, making this point. It seems that the memorization of the parameter, the memory is stored in the parameters of specifically the feed-forward layers, and it comes from the fact that in higher dimension space, 2 random vectors are likely to be almost orthogonal. So suppose you take 100 dimension space, you don't just get 100 orthogonal vectors. The spanning vectors is not 100, just 100. But if you're willing to be a little bit approximate and say, well, almost orthogonal is good enough, then you have a fairly high orders of magnitude, high number of vectors that are all almost orthogonal. And so that leaves for a, in a sense, creates a vector space in there in which a lot of information somehow can be stored. And so, nevertheless, the fact is that LLMs have parametric memory. Now comes the interesting thing. If traditionally, without RAG, if you just have a LLM, let me call this the no RAG system, that because that's the wording this paper uses, and then you give it a query, it will answer it. So this will be directly using the parametric memory. Now, the argument for RAG has been as follows. The first is that LLMs are trained only on publicly available data. So it is not aware of your company confidential data, your company proprietary data. That's one argument. The second argument is the sheer size of knowledge that is there keeps on exponentially growing. And there may come a day in which we may not be able to train the LLMs on exponentially growing data sets. Actually, at this moment, we seem to be having the converse problem. We are not getting enough data. We are feeding it synthetic data to train. But one can hypothesize that there may come a day. The third reason is that LLMs are terribly expensive to train, so they are dated. So suppose you train an LLM, let's say Llama 3.2, and it was trained, let us say in July of 2024. I don't remember the exact date, but let's take it for granted that it was trained in July 2024. What it means is all the facts that have happened thereafter, right, it is not aware of. And so all the news articles, all the things that have happened, it cannot answer questions about. Nevertheless, if you could search the web and use the entire web and therefore the news sources as one of the search indices, call it, then of course you can pass that information to the LLM and say, well, here is a query, here is the relevant information, and could you use this information to answer the question? And the LLM would be pretty capable of doing that. It will pretty much trust the information you do, and therefore you say that you can what the LLM doesn't know, you can augment it. Augment from what? Retrieval from search results. The word for search in the industry is retrieval systems. So you say retrieval augmented generation, and therefore this is the other perspective, that the LLM is generating an answer not only based on facts from its parametric memory, but also from facts that has been retrieved from various search indices, right? And it is putting it together. So that does sound very good in theory. In practice, it brings about a host of problems. As any one of you who has been doing RAG knows, that RAG is a wonderful idea in theory, but its implementation can be very, very frustrating. Almost there is an old saying that I keep quoting from Tolstoy's famous book Anna Karenina. Anna Karenina starts with the famous sentence, the novel, all happy families are alike. Each unhappy family is unhappy in its own unique way. To the extent that RAG is being implemented in just about every corporation, every academic institution, everywhere where there is information, It is the poster child of generative AI these days, the most used solution coming from generative AI, vast adoption. So every company is adopting RAG, but if you go and talk to all of them, they are all, to various degrees, unhappy families, because everybody's RAG implementation does leave a lot of scope for improvement. So it is not something that comes without its limitations. But like all things in engineering, it's a compromise. It's a compromise between how much compute you are willing to throw at it, how cleaner data you want to bring to it, and what are the extent limitations of the LLM. Now, this research paper in particular addresses one fundamental problem. It says that suppose you bring this information coming from the retrieval. Let me just say that some bits of information is coming from retrieve information. You feed this along with the query to the LLM. But the LLM in its mind has an answer to the query, information in its parametric memory, information pertinent to query. It may have information of its own. It may have an answer of its own that it can dig out from its parametric memory. What if there is a contradiction between the two? And does that contradiction happen? So it turns out that these contradictions are actually very common. And anyone of you who are doing RAG systems, it is very frustrating actually, because if you have candidate, let's say candidate's retrieval result C1, CK, all the way to CN, and then you have, let's just say that the LLM could generate not just one answer, but let's say that it could generate, let me call it L1 to, let me say L10, 10 possible generations or 10 possible ways it could generate the answer. Why 10 answers? Because, well, you can keep asking the LLM the same question over and over again, and it might come up with 10 different variants. Hopefully, most of them saying the same thing, but you never know. Now you do have you can have a contradiction table. Any one information, for example, CK might contradict, and there may be crosses here and there. These facts, first of all, they may be so contradictions go like this. You could lay the C1 all the way to Cn and L1 all the way to L10 into a giant matrix. And then what happens is that there will be contradictions all over the place. So for example, the Ci and Cj, the retrieval results may contradict. Hopefully, sometimes it happens, though not commonly, but even the LLM generation may contradict also each other, or some of the results, some candidate results from retrieval may contradict some answer from the LLM, right? So you see the problem, one of the core problems with RAG has been, what if you're dealing with contradictory information? What if, for example, the LLM believes that the Earth is round, right, or spherical, but you're feeding it information which is actually saying that the Earth is flat. Now, just posit the situation that you managed to search something about the topology of the Earth, and there were some sarcastic articles or parodies. You see on the web a lot of parodies of people who used to believe that the Earth is flat. Well, it turns out that there are people who still believe that, but you can write, a lot of people can write humorous or parodies on the belief that the Earth is flat. And they may show up in the search result. If they do show up in the search result, now the LLM has a problem. Internal knowledge is telling it that the Earth is a sphere. External search results are telling it, because obviously the search engines don't understand irony, they don't understand satire. They may be retrieving the fact and saying the Earth is flat. What is the LLM to do? These are typical situations where RAG results degrade severely. So that is the problem. That is the problem they are going to address. How can you address the problem? That's a statement. Now let's go and read this paper and see what exactly do they do to address it. I'll start with the abstract. Retrieval augmented generation, while effective in integrating external knowledge to address the limitations of large language models, can be undermined by imperfect retrieval, which may introduce irrelevant, misleading, or even malicious information. I will go a little bit further, by the way. This paper does not mention that sometimes you ask the LLM the same question and it may contradict itself in the next answer. Right? So that part they haven't really addressed, but it turns out that the solution would nevertheless work even in that situation, and it would solve that solution, that problem also. Despite its importance, previous studies have rarely explored the behavior of RAG through joint analysis on how errors from imperfect retrieval attribute and propagate, and how potential conflicts arise between the LLM's internal knowledge and external sources. So this is what we are saying, and what they are saying is nobody has really studied it systematically. We find that imperfect retrieval augmentation might be inevitable and quite harmful through controlled analysis under realistic conditions. So they say that fact is, when you retrieve external information, sometimes you can't avoid contradictions. Right? So, for example, if you're searching, one search index belongs to one point of view, another search index belongs to just the opposite point of view, well, of course, it's a no-brainer that you'll have contradictions. We identify the knowledge conflict. So they introduce a term here, which is important, a knowledge conflict between LLM internal and external knowledge from retrieval as a bottleneck to overcome in the post-retrieval stage of RAG. So this is a core problem, they have to say. By the way, what they call internal and external knowledge, again, these are different words to say parametric memory and retrieval data, retrieval memory. Okay? To render LLM's resilience to imperfect retrieval, we propose Astute RAG, a novel RAG that adaptively elicits essential information from LLM's internal knowledge, iteratively consolidates internal and external knowledge with source awareness, and finalizes the answer according to information reliability. So what they're saying is they're going to go through an adaptive and iterative process to take all of this knowledge and somehow resolve the conflicts and come up with a much better answer. Now, I would like to, in this context, mention a word that I mentioned last week also, and I've been saying this, that these days there is a huge movement of algorithms or techniques that do what I call inference-time compute, and broadly, inference-time compute. And these broad inference-time compute approaches are to be distinguished from training-time compute. Remember, when you train up or pre-train a language model, you are at the mercy of the neural scaling laws. You want the model to be more capable, and then you need to bring more data. You need to build a bigger model, and you need to train it for much longer. The inference-time compute, you see that this year, 2024, has been getting a lot of traction. What it says is, what if we could take a LLM with all its blemishes, with all its problems, with all its hallucinations? Can we do something at inference time such that its performance is significantly better? Right? And within that category, I would put things like agentic reasoning, agentic frameworks. I would broadly even put RAG under in the same category, but I would certainly put high-end prompting techniques in that category. And this paper is actually, it is this prompt that we talk about that synthesizes all of this information together. It is an iterative prompting process, as you will see. So what we are doing is, and as has become common practice these days, you never take the answer straight from the LLM and say, okay, here it is. But what you do is you go through a few iterations, and you have a clever way to iterate over it a few times and do things, and then take a final answer and give it. Right? Now, those of you who are familiar with multi-agent systems, task decomposition, and prompt self-refinement, and so on and so forth, we are all talking about similar things within the bag of inference time compute. So I'll leave that thing on the table, and I would say that this falls within the same general category. Now, continuing the rest of the abstract, to render LLMs resilient to imperfect retrieval. So this is the important thing. We propose Astute RAG, a novel approach that adaptively and aware with source awareness. So one of the things they do is they also look at the reliability of the source. Where are you getting this information from? Right, the provenance and so forth. Our experiments using Gemini and Cloud demonstrate that that Astute RAG significantly outperforms previous robustness enhanced RAG methods. So obviously people have been trying to fix RAG for a lot of times. There is robust RAG, there's instruct RAG, there is this, there is that. There are many such techniques, so which have been in practice, but what they are saying is that this achieves a new state of the art and how well it can perform. Further analysis reveals that Astute RAG effectively resolves knowledge conflicts, improving the reliability and trustworthiness of RAG systems. This is the most crucial thing. If you can resolve knowledge conflicts and improve the reliability and trustworthiness of RAG systems, you're going to the core of a deficiency that you currently face with RAG. And that is why I thought this paper was very relevant and of practical use to a lot of you, because I would guess all of you are doing RAG in some form or the other. So I won't go into this paper line by line, but I'll go through the figures because I've explained the main idea. What it's saying is that, see, when you have results coming in, you can have two kinds of facts. Either the search result facts are correct, they call it the RAG facts. RAG is correct. Or the LLMs, internal, actually I take a little bit of an exception with the language they use. They should have said RAG's internal memory or internal knowledge or search retrieval results is correct or not. But anyway, be as it is, these are the words they use. So what they are saying is that if you look at the search results that you feed into a RAG pipeline, into an LLM, it is only 45% of the time they observe statistically that the two agree. So think about it. We have all been using RAGs and building RAG pipelines for quite some time. And yet now this paper is reporting through a very careful analysis that actually half the time the retrieved result contradicts what the LLM knows, right? So that's pretty bad, right? That in itself actually is a cause for attention. And then what makes it even, I'm sorry, I take that back, 35%, not 45%, 35% of the time, you have a situation where neither RAG, actually I take that back, what was I saying? 35% of the time, it is as bad as RAG, the LLM is wrong and the facts are wrong or irrelevant. Right? So there is no way that you can combine them. Only 45% of the time, you have a situation where LLM, the facts coming from search and the facts coming from LLM or understanding of LLM, they resonate with each other and they happen to be correct. Right? So what it means is that the remaining 55% of the time, more than the majority of the time, you have a real problem, isn't it? Because if you say that this is what you were hoping for, then obviously you agree you don't want this, you don't want this, and you don't want this, right? So what are the other situations? Your search results are good 9.1% of the time, or sorry, wrong, but the LLM is correct. And you can have the converse situation. The LLM is wrong, but the search results could have potentially corrected the LLM. So they give examples of this. They say, previous work leveraging RAG. So you may have an example which they give here. Zonia received from Ruben a letter in the play. And then, but this is what the LLM thinks. But the database is correcting it and saying, Zonia received from Ruben a kiss in the play. Now we have a problem. These two contradict each other, but question is which one is right? Do you take the answer? The LLM now has to figure out. LLM thought it was a letter. Database is saying it's a kiss, and you have a contradiction. Likewise, you take this other example. China's one-child policy ended on January 1st, 2016. So the database, on the other hand, the search index, is saying China announced the end of one-child policy in late 2015. Right? So it turns out that the LLM is correct and the database has old information or incorrect information. And then, of course, you do have a situation where both of them are wrong. 35% of the situation, both of them are wrong. Right? Now the question is, what can this paper do? This paper will try to create things that will improve this situation and this situation, and will claim that you can improve the 35.4%, that situation where both are wrong, also in some sense. So how does it do that? How does it deal with the contradictory information? The so-called knowledge conflicts is the crux of what this algorithm is. So I will just jump ahead straight to the algorithm. But before I go into the algorithm, so it's a very simple algorithm. What you say is that, let's say that you ask the LLM for information. I'll just give you one pass because it has multiple time steps to it. So you ask the LLM, here is the query, go generate an answer from your internal knowledge. So it may generate these documents. It may generate these documents or these answers. You take these answers, right? And then what do? You go to your RAG system. You also take your search engine and you get the search results. And now put all of these together into a giant pile. So this giant pile of information or answers contains candidate answers that the LLM has partly generated and the search engines have partly generated. But then you go to the next step. In the next step, what you do is you start grouping the answers. You ask the LLM using a prompt, and just a prompt. The beautiful thing is all they do is they write a very clever prompt or a nice prompt, simple prompt actually, to group the answer into consistent piles. Do you notice? Now, when you group it, it doesn't matter whether the answer came from inside the LLM or it came from search results, but you create clusters. Think of it this way, that you create one cluster, one of documents, which are, let's say that some documents are coming from the LLM and some are coming from the search results, and one more document and maybe some here and so forth. And let me just give it a name. These are from the LLM, these two, and these are coming from search results, search. But these are consistent. And then you can create another file with similar results such that they are all consistent. And then you might end up with a document, a single cluster with just one document. Let's say just one document. And then you might end up with, in the search results, documents that are just irrelevant, right? That is what they are pointing out here. So now what do you have? If you look at this carefully, there is a set of one consistent cluster, another consistent cluster, and then a third consistent cluster, or maybe they're documents that are, well, okay, you group it together. Now what do? You notice that this cluster and this cluster, what they are saying, they are non-conflicting. They're additive. In other words, you could add this information into a collective cluster. But this cluster, the in-between cluster, is a conflicting information. So now what have you got? wherever the clusters could be merged. So first you create clusters of information that pretty much are consistent with each other. They're pretty much saying, or in common sense word, they're saying essentially the same thing. And then what do? If two clusters don't contradict, they don't conflict in their information, then the next level, you merge them. And so at the end of it, you would end up with a set of clusters, maybe in this particular example, just these two clusters, 1 and 2, except that 1 and 2 contradict each other. Right? Now what do? What you do is, based on the source of the information and reliability and so on and so forth, and based on a bunch of heuristics, and this is where at this moment I would say that there is no perfect way. It's an improvement, but there is no perfect way. You need to pick one of the clusters to answer the question, right? To answer the query. And so what they do is they use a scoring method. They score it. They ask the LLM to score to this and score 1 and score 2. Let's say 1, 2. Reliability score. You create a reliability score. Which of the answer do you have more confidence in? And you let the LLM think through and pick one. And if you do so, they find actually that even in contradictory situations, it tends to pick the right answer 80% of the time. I believe that's the number I saw in the paper, which is impressive because at this moment, nobody is doing that. The LLM is supposed to synthesize all the search results. So it scratches its head and then comes up with some polite answer, diplomatic answer that puts all those points of views together, and it doesn't make sense. But here, you're asking the LLM to pick and choose things that it could merge, it merges. But after that, if you have conflicting clusters of information, then it has to go and use a scoring mechanism to do that. And the beautiful thing, and so this is what this algorithm is written out in a more formal algorithmic notation that you're familiar with from your algorithmic textbooks. So this is it. Now, before I go any further, you would say, wow, this is amazing, but what did they do to do it? Actually, what they did is simplicity itself. Look at what they did. For the prompt, so they have 3 prompts: a prompt to generate, prompt to consolidate, and prompt to answer the question. Let's look at the prompt to generate. It says generate a document. So given a user question, generate a document that provides accurate and relevant information to answer the given question. If the information is unclear or uncertain, explicitly state, I don't know, to avoid any hallucinations. So this is as simple as asking, see, you realize that, sorry, this part is essentially a non-RAG. You're asking the LLM, I'm not giving you any search results, just go answer this question, if you can. If you can't, then say, I don't know. Then is the iterative part. You take, and you can from this generate a few documents from it. Now you go to you go and mix it up with all the search results, and then you get the consolidation task. What is the consolidation task from? You're saying consolidate information from both your own memorized documents and retrieved documents in response to the given question. Now, one important point that you don't see in the prompt is when you are given information, it also gives you the source of the information. It says this piece of information, this document is from the LLM, this document is from the search result, and from the source of the search result. So now, these are the bullet points. It says, for documents that provide consistent information, cluster them together and summarize the key details. So what you do, you cluster and you rewrite key details into a single concise document. What it means is that let's go back here. Once you have clusters of consistent document, you in effect replace this, you take all of these and then you replace it with rewrite to a single doc. Likewise, this consistent cluster will get another single doc, and this will become another single doc, and things that you find to be irrelevant, because LLMs do. Now see, the reality is whenever you search, you're not going to get perfect precision, right? You will get irrelevant things in your searches. And LLMs are usually good at figuring out which of the pieces of information may be irrelevant. So you have it just rejected. Then once you have a rewrite, it is the rewritten docs, let me call it A and B and C. Let's say that A and B are non-contradictory. Then you merge A and B, right, into this first result, and then you, because C contradicts, you merge it in this result, and now you have another rewrite, and now you ask the machine. So you see that you're just prompting, you're going over and over to the LLM, asking it to rewrite, to merge, to consolidate, right? And that's a cycle that you're doing. As simple as that. If you read the prompt, I think even the math looks a little bit jargonish. There's nothing fancy about it. For documents with conflicting information, separate them into distinct documents, ensuring each captures the unique perspective of the data. Exclude any information irrelevant to the query, and blah. For each new doc, clearly indicate whether the source was from memory or an external LLM, the original document numbers for transparency. So in other words, give the provenance of the thing. And this is it. And finally, it says propose answers and assign confidence, how confident you are. And then the rest of the prompt is, just outputting it, the mechanics of outputting it. So does this simple approach work? And I find this to be actually brilliant. I don't know why we are all doing RAG. None of us thought of it. But it's amazing that these guys thought of this simple but elegant solution. It doesn't completely solve the problem, but it does make it much better. So let's look at the results. When you look at the results, you see that, let's look at these results very carefully. There has always been a problem. Sometimes RAG, if it brings contradictory information, not only can it not improve your answer, it is worse than just using a LLM without a search engine backing it, right? And you see that sometimes. Look at this. This is just the LLM. No RAG means just the LLM. And do you notice that when you do have, there are situations where, especially these two situations, pay attention to this. What does it mean? RAG underperforms no RAG, isn't it? And it's an interesting thing why we never noticed it. The 44 is the score with RAG, 47.12 is the score. And what they're saying is the reason you may not have noticed it is because people haven't looked at it in the real world circumstances. So what do they define real world circumstances or realistic situations? Well, their definition of realistic situation is that their search index is the Google search, right? They are treating the entire Google search engine as their retrieval or as their search index. So they're saying, given a query, you can Google up, get results, pick 10 results from those, use those 10 results, those 10 documents, and feed it in as the RAG part, right? And what they're saying is sometimes what the LLM internally knows is better than what a query returns from the search, from Google search. And there can be a variety of causes. Badly written queries is obviously a nuisance. Those of you who run RAG systems know that it is a folly to not do query rewrites, right? Because users are notoriously bad at giving queries. Right? That is a whole area, subfield within RAG itself, and a technique that we teach, for example, here at Support Vectors in a course which we humorously call RAG to Riches. Advanced techniques and best practices. So one of the best practices we teach people is you must, and we take them through boot camp and labs and so forth. We show them that you must always focus on query rewrite as one of the things, because users are notoriously bad at queries. But for whatever reason, there are situations under real world condition where no RAG, just a LLM can do better than a RAG, right? Under realistic situation. But now, what is the situation? So I'll just focus on that, and I'll just look into, on the other hand, the end result. So as you can see, it's not that people are not aware of it. When you look at it, there has been progress happening over the years. People have been trying all sorts of things: robust RAG, instruct RAG, self-route, blah, 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 right? Nevertheless, what this simple method with prompting that they have created, which they call Astute RAG, look at their numbers, right? Look at their numbers. That if you go through this process, this 3-step process, you get state-of-the-art results for RAG. Now, by the way, these numbers are a material improvement. To get this level of improvement is significant. I wouldn't say that it is completely cracked the problem and made a huge improvement, but I would say that if you know RAG and if you read this paper, you would say, oh my goodness, why didn't we think of doing it ourselves? And well, it turns out that these clever guys discovered the technique that I suppose in hindsight looks like we should have done that. So that is it, guys. That is the gist of this paper. If you look at the further results, everywhere you see that compared to anything prior, these lines are where all the bold, if you notice all the bold numbers, which are the state-of-the-art results, are here with Astute RAG. Right? So in one paper, they seem to have managed to outdo. Robust RAG, by the way, it was a strong contender. Instruct RAG was also a strong contender. I would say that compared to Instruct RAG and Robust RAG has been very good. The fact that they can beat those techniques, which are just now developed just a few months ago, this is quite remarkable. And that is it. That is the thing. And you see it in all situations. So now this result is interesting. Actually, there is one result that is very interesting that I should have covered. This result. One of the things that you notice is that retrieval precision. What is precision? Your search engine, how often, let's say that you get 10 results, how many of the results actually are relevant to answering the question? Or are they just irrelevant facts? Right? That is a relevancy problem. There's a precision problem, right? It's nothing to do with the LLM itself, but is that imperfect retrieval, what they point out, is the cause of a lot of problems, right? And obviously, if you have experience in this domain, you know that. Right? Sometimes you throw an entire team's index and you tell the team to go curate better documents into the index, if it is an intranet, if it is within the enterprise. Right? And how often it happens? Quite often, actually. A retrieval precision, shockingly, 0%. How often you get no good result, no relevant fact or correct fact in the search result, 34% of the time in one data set. In another data set, 18% of the time, 25. So they average all of it out to about 20% of it, 19 or 20% of the time. They say that RAG systems are pulling in realistically results that simply are irrelevant to the question being asked. Right? And you have to function in that environment. Right? And that is the formula, the number of retrieved passages containing correct answer over the total number of retrieved passages. And this is specifically an overall 20% answers. Yeah. 20% cases are so bad that there is not a single answer within any retrieved passage. Right? And that's reality. You know, it is holding up interesting insight into reality. And then you look at retrieval, and it is comparing itself to other state-of-the-art methods. Astute RAG has been compared to Instruct RAG, self-route, etc. And you say that now observe something very good. First, let's look at it from this side, from the right-hand side. We'll start looking at it. Notice that worst case performance on the benchmark, you take those cases where the data set, which are really, really hard for RAG methods, such that baseline RAG gets it right only 20% of the time. We do know that Instruct RAG is a very powerful method. Most of you are familiar with it, perhaps. It takes the accuracy from 20% to 60%, which is most impressive. Self-route also is in the same ballpark, 60, maybe let's grant it 65%. And then you look at Astute RAG, which is just shy of 80%. Right? Quite remarkable. Now, let's look at the second graph. It says, what is the accuracy when both the answers are correct? When both answers are correct, as you can imagine, Astute RAG is not going to contribute anything new. In fact, they are all at par, though if you notice carefully, Astute RAG, for whatever reason, seems to be just a tad bit lower than self-route and Instruct RAG. But on the other hand, when the information is contradicting, notice that Astute RAG beats the best methods available so far. In fact, methods that just came out a few months ago. And when both, now here is the interesting part that I want to bring out. When both the answers are incorrect, when retrieved results are wrong and LLM's understanding is wrong, it turns out that when you do Astute RAG, because it is able to figure out and understand that there is a problem, it gives an answer which is more accurate. Perhaps it will say that they are contradictory statements, whatever it is, right? And so that is the main thing about this paper that it brings out. Let me see if there's any other result that this paper can bring out. Other than that, yeah, this is it. So let's go through the conclusion. Our paper investigates the impact of imperfect retrieval on the performance of RAG systems and identifies knowledge conflicts as a key challenge. And that certainly is true. I mean, this is something all of us doing RAG are well aware. It's such a nuisance. I mean, in practical terms, we face it. But we face it, and I've always attributed it to the fact that people, basically, because we deal with enterprise knowledge, you often find documents, especially product documentation. One version of the product, another version of the product will actually contradict each other for obvious reasons, because the next version of the product behaves differently. And so what do you do? What do you do when you put a RAG on it? The documentation of the product, you put it into a RAG system. To address this, we introduce Astute RAG, a new novel approach that leverages the internal knowledge of LLMs and iteratively refines the generated response by consolidating external and internal knowledge in a source way. I don't know, in a systematic way, perhaps is what they meant. Our empirical results describes, and now they mention, nice of them to mention that there's still a problem. Amongst the limitations, the Astute RAG's effectiveness hinges on the capability of advanced LLM with strong instruction following and reasoning abilities. Hence, potentially more limited applicability with less sophisticated LLMs. Why is that relevant? See, these days, there is a prevailing belief that because we are using RAG to just explain the search results, therefore we don't need very powerful LLMs. It is a fact, actually. Now, problem is smaller LLMs, they don't have much advanced reasoning capabilities, instruction following capabilities. You give it a long instruction and it actually doesn't work. So, by the way, I tried to play in a very preliminary way. I tried to play with this, and I noticed that when I did it with a 70 billion parameter model, it seems to work fine. Right? I tried it with a 2 billion parameter model, and it wasn't. You couldn't use this technique. It turned out that I mean, I don't know. It was inconclusive whether it was actually improving or not. But my results were just very preliminary and very quick one. So that point holds. Obviously, if I had tried it out with cloud or something, I just take it on faith that it would be even better. But 70 billion for me worked. As an important future direction, extending the experimental setup to include long outputs would be important, where the challenges of imperfect retrieval may be even more pronounced, so on and so forth. So you always end a paper by saying what further work can be done, what remains to be done, and so forth. And so it does it. Now, if you go and look at the references, you will find all your familiar friends there. Most of you, for example, are familiar with this paper, self-RAG, right, through self-reflection. This is what we do. Now, by the way, if one of the interesting things they do is constitutional AI, harmlessness from AI feedback. This is one of the important things. What do you mean? You put in your prompt the fact that, guys, if you don't know the answer, say so, and so on and so on. Be correct. Evaluate and understand large. I mean, the rest of it is benchmarking. By the way, this paper uses a benchmarking called RBG or RGB or something like that as a benchmark. We don't use that. We use I mean, of course, here we use ruggers. I think, internally here, and so on and so forth. So that is it. I don't know what else to point to. It's a simple paper with a simple idea, but a very, very clever, very insightful idea that can make practical difference to all of it. Guys, do you realize that this is just prompts that go into the RAG end, the prompt part, template of your RAG, which means that you don't need another model. There is no code there. There's nothing. It's just with prompts, they managed to pull up a significant or a material improvement so that they achieve the state of the art. That's all it is. And with that, I'll end my paper reading. I'll take questions. Any questions, guys? I thought after all the mathematical papers we were doing, it was time to do something simpler. Any thoughts? Any opinions?
That was pretty good. Yeah, I think it was a very good paper.
Yeah, thank you, Mike. Anyone else, guys, with questions, with anything? I hope you like the choice of the paper. I picked it up because of its sheer practical applicability. Easy to apply, makes a difference to something we all are doing. And so let's go and use it. All right, guys. And so I'll stop the recording or the live streaming.